Welcome back to Physical Science 101. We have been talking about thermal energy, and we're going to continue to do that with a lot of exercises today. So let's get started, and let's put what we covered in the last lesson to work. Here's our first question. An electric current heats a 0.221 kilogram copper wire from 20 degrees C to 38 degrees C. How much heat was generated by the current? The specific heat capacity of copper is 340 joules per kilogram degrees C. So I would like you to pause and work on this and do as much as you can, and then when you're ready to see me work it, come back. Okay, here's the situation we have from an energy diagram. Okay, we have a box representing copper, and we are bringing in heat into the copper, and the result of bringing heat into the copper is that our internal energy is increasing. So that is our energy diagram. We're bringing heat into the copper, and that is increasing the thermal energy of the copper. From the first law of thermodynamics, the heat is equal to the change in the thermal energy, or the change in the thermal energy is equal to the heat. And we also know that the change in thermal energy, since the temperature of the copper is increasing, the change in the thermal energy is equal to the mass times the specific heat capacity of the copper times the change in temperature. So what is the change in temperature? The change in temperature is 38 degrees C, where we wind up, minus 20 degrees C, where we started. So that would be 18 degrees C. The specific heat of copper is given to us. That is 340 joules per kilogram degrees Celsius, and the mass is also given. That is 0.221 kilograms. So it's everything we're given, and this is our physics. So we have the heat is equal to the change in thermal energy, which is equal to the mass times the specific heat capacity times the change in temperature, and we know all of this, so we can go ahead and put them in and calculate. 0.221 kilograms of mass times 340 joules per kilogram degrees C times a change in temperature of 18 degrees Celsius. So our heat, if we work the numbers, is 0.221 times 340 times 18. 0.221 times 340 times 18 is equal to 1,353. And what are our units? Kilograms cancel out, degrees C cancel out, and our units that we're left with are joules. So the heat that was introduced to raise the thermal energy and raise the temperature was 1,353, or you could even round that off to 1,350 joules of heat. And that is what you were asked for. All right, here's another exercise. Two samples. 0.5 kilograms of sand, where the specific heat capacity of sand is 840 joules per kilogram degrees Celsius, and 0.5 kilograms of water, where the specific heat capacity of water is 4,184 joules per kilogram degrees Celsius. Both have an initial temperature of 20 degrees Celsius. They are placed in the sun, and both receive 10,000 joules of heat from the sun. what is the final temperature of each sample? Okay, so once again, I'd like you to work through this, and pause, work through this, and come back when you're ready to see me work it. So go ahead and pause, please. Okay, let's do an energy diagram for each one of these. Well, both are actually the same. Both are the same. We have heat coming in. We have some heat coming in, and we have thermal energy increasing. And the thermal energy is increasing with an increase in temperature, so our equation that we're going to use is that the heat is equal to the change in thermal energy, and the change in the thermal energy is equal to mass times specific heat capacity times the change in temperature. That is the same for both the sand and the water. The only difference is the specific heat capacity is different for both. So let's do one for sand and one for water. Okay, for both of these, the mass is 0.5 kilograms, and the heat is 10,000 joules, but we have different specific heat capacities, and I'm going to write them into here. Okay, so we have heat is equal to mass times specific heat capacity times change in temperature. I'm looking for change in temperature, so I want to get change in temperature by itself, so I'm going to divide by mass and specific heat capacity. So those cancel out, and now I have my change in temperature is equal to the heat over mass times specific heat capacity. For the sand, the change in temperature is the heat of 10,000 joules over a mass of 0.5 kilograms and a specific heat capacity of 840 joules per kilogram degrees Celsius. Okay, for our units, we have joules divided by joules, those cancel out. Kilograms divided by kilograms, those cancel out. And we're left with 1 over Celsius in the denominator, which when we bring up to the numerator, will give us a change in temperature in degrees Celsius. Okay, so how many degrees Celsius? Let's do our numbers. 10,000 divided by 0.5 and also divided by 840 joules per Kelvin degree C. Now remember, since you're dividing by both of these numbers, you either need to put the division sign twice, so it'd be 10,000 divided by 0.5 divided by 840, or you need to put parentheses around your whole denominator. So it'd be 10,000 divided by parentheses 0.5 times 840 and a closed parentheses. And if you do that, you should come out with 23.8 degrees Celsius. So the sand changes by 23.8 degrees Celsius. So the final temperature, which is what we're actually asked for, so the temperature, the final temperature is 23.8 degrees Celsius plus the 20 degrees Celsius we started with, which would be 43.8 degrees Celsius. That is for the sand. Now the water, we have the exact same thing. the change in temperature is the heat over the mass times the specific heat capacity. So the change in temperature is still 10,000 joules divided by a mass of 0.5 kilograms. But this time, the C is different. It's 4,184 joules per kilogram degrees Celsius. So the change in temperature this time would be 10,000 divided by a half divided by 4,184, which is a much bigger number than 840. So we're dividing by a much bigger number, so our change in temperature is much smaller. It's 4.78 degrees Celsius, which is what we're left with when we cancel out our units. So the final temperature of the water is the 20 degrees that we started with, plus 4.78 degrees Celsius. So the final temperature is 24 point, and I'm just going to round that up to 8 degrees Celsius. So you can see that the final temperature of the water is going to be much less than the final temperature of the sand, even though they receive the same heat, because the specific heat capacity of the water is much greater than the specific heat capacity of the sand. So those are the answers for both the questions, and now you know why at the beach the sand is much hotter than the water on a sunny day. Okay, here's another exercise. A 0.1 kilogram sample of metal is warmed 20 degrees Celsius when its thermal energy increases by 251 joules. What is the specific heat capacity of this metal? So we're going to work this exercise just like we worked the previous ones, but now we're looking for the specific heat capacity. So as usual, I'd like you to work through this as best you can, and then pause and come back when you're ready to see me work it. Okay, we're going to work this just like we worked the rest of them. We have a box representing the energy of the metal. We have heat coming in, thermal energy increasing. The heat is equal to the change in thermal energy, and the change in thermal energy is equal to mass times specific heat capacity times change in temperature. The mass is 0.1 kilograms. The change in temperature is 20 degrees Celsius, and the heat is 251 joules. Okay, so heat is equal to mc delta T. This time we are looking for the specific heat capacity, so we should divide this by mass and change in temperature. We'll divide heat by mass and change in temperature, so we have heat divided by mass and change in temperature. Mass and change in temperature cancel out, and we're just left with specific heat capacity on this side. We know all of this. Heat is 251 joules. Mass is 0.1 kilograms, and change in temperature is 20 degrees Celsius. That's equal to our specific heat capacity. Our numbers are 251 divided by 0.1 and also divided by 20. So that would be 125, or well, I'm going to go 125.5 joules per kilogram degrees Celsius, so now you see where those units come from, is our specific heat capacity. So this is the kind of experiment that you might do in a laboratory. So that is it. That is the specific heat capacity of the metal, and that's what you were asked for. Okay, here's another exercise that is similar, but a little bit different. And the question is, how much heat is needed to melt 0.25 kilograms of ice at 0 degrees C into water at 0 degrees C? So this is similar in that we have heat going into an object and increasing its thermal energy. It's different because that increase in thermal energy does not appear as a change in temperature, but it appears as a change, as a phase change. So you will have to use your equation for a phase change, and you will also have to go back and look up the proper latent heat of water. So try that. Do your best with that. Try that. Pause and work on it, and whenever you're ready, I'll be here working it for you. Okay, our situation is similar in that we have heat going in and an increase in thermal energy. So the heat is equal to the increase in thermal energy, but the increase in thermal energy is now represented by mass times the latent heat of fusion, since this is melting. Okay, and what do we have? We have a mass of 0.25 kilograms, and the latent heat of fusion of water is 334 kilojoules per kilogram. Okay, so heat is equal to mass of 0.25 kilograms times 334 kilojoules per kilogram. Okay, so the heat, multiply those two together, is 0.25 times 334. That is 83.5. Kilograms cancel out, and my units are kilojoules. Okay, so it's 83.5 kilojoules of heat. Now, if we want to convert that into joules, we would have kilojoules in the denominator and joules in the numerator, so that kilojoules will cancel out. And 1 kilojoule is 1,000 joules, so my kilojoules cancel out. So in joules, the heat would be 83,500 joules. And that is the answer that we're looking for. Okay, here's another question. How much energy is needed to heat 0.25 kilograms of water from 80 degrees Celsius to 100 degrees Celsius and then vaporize it into steam at 100 degrees Celsius? Okay, so this is a two-part exercise. First, you have to add heat and increase the temperature, and then you add heat and have a phase change. So you will have two terms to add together, one related to the change in temperature and one related to the phase change. So you will have to have the correct specific heat capacity of water for heating and the correct latent heat of vaporization for changing water into steam. So try that, do what you can, try that, and then when you're ready, come back and watch me work it. Okay, our energy situation is as it always is. We have heat going into the water, and we have an increase in thermal energy. The heat is equal to the change in thermal energy. And the thermal energy now, the thermal energy is equal to the mass times the C times the change in temperature plus, so that is for the warming of the water, plus mass times the latent heat of vaporization, that is for the phase change. So this is for warming, and this is for the phase change. Okay, when we warm, well, let's start with the mass. The mass is 0.25 kilograms of water. When we warm, the change in temperature is 20 degrees Celsius from 80 to 100. And so the mass is 0.25 kilograms. The specific heat capacity of water is 4184 joules per kilogram degree C. And the change in temperature is 20 degrees C. And then we have to add 0.25 kilograms times the latent heat of vaporization of the water, which is 2,260 kilojoules per kilogram. So we're going to have to be very careful with our units. Okay, so let's work this out, and we're going to keep these two terms separate. Okay, that's 0.25 times 4184 times 20. That is 20,920. My kilograms cancel out, my degree C cancel out, and this is in joules. And then over here, I have 0.25 times 2260, and that's 565 kilojoules. Notice here we have joules and here we have kilojoules, so we have to be careful. We're going to have to convert these kilojoules into joules before we add these two terms together. Kilojoules in the denominator, joules in the numerator. 1 kilojoule is 1,000 joules. Cancel off my kilojoules. And so my heat is 20,920 joules plus 565,000 joules. So now that I have joules and joules, I can add these two numbers together. I can add 20,920 plus 565,000. And that is going to be, I'm going to round off to the nearest thousand. That is going to be 586,000 joules. So be careful about your kilojoules and your joules. If you add two numbers together, they all have to be in the same units. And so that is the answer that we were looking for. Now notice one thing. Notice that it takes an awful lot of energy to vaporize water. So this is the amount of energy it took to warm the water by 20 degrees. And this is the amount of energy that it took to vaporize it. It takes a lot more energy to vaporize the water than it does just to warm it up. Okay, here's another question. A 1,000 watt kettle is used to heat 0.5 kilograms of water from 20 degrees C to 100 degrees C. About how many minutes did this take? Now first, remember that when we're talking about 1,000 watts, we're talking about power. So this is going to be a question where you have to use power. And remember that power is heat divided by time. So that's how we're introducing time into this. We're introducing time into this with power. Power is heat over time. So the first thing you have to do is you have to figure out how much heat it took to heat 0.5 kilograms of water from 20 degrees C to 100 degrees C. Now this is actually a question and an answer that we're going to test using this 1,000 watt kettle, which is filled with a half of a kilogram of water. A half a kilogram of water is a half a liter of water, and that's what I put in. And that water is currently at room temperature, which is 20 degrees C, and we're going to heat it to 100 degrees C. So first, let's make our prediction. We're going to make a prediction, and then we're going to test it. So first, I would like you to try working this. Do your best, pause, and come back when you're ready to see me work it. Okay, our situation is the same as always. We have thermal energy increasing we have heat increasing our thermal energy. So the heat is equal to the change in internal energy, which is equal to mass times specific heat capacity, times change in temperature. Mass is 0.5 kilograms. Change in temperature from 20 to 100 is 80 degrees Celsius. And our specific heat capacity is 4,184 joules per kilogram degrees C. So the heat is 0.5 kilograms times 4,184 joules per kilogram degrees Celsius times 80 degrees Celsius. So our heat is 0.5 times 4,184 times 80. That is 167,360 joules. 0.5 times 4,184 divided by times 80. Okay, so that is the heat that we need. Now remember that power is heat over time. Heat over time. So we want to get time by itself, so we'll multiply both sides by time and then divide both sides by power. So our power cancels out here and our time cancels out over here, and we're left with time is heat over power. Our time is 167,360 joules divided by 1,000 watts. So the time will be 167 seconds. If we want to convert that to minutes, put seconds in the denominator, minutes in the numerator. 1 minute is 60 seconds. So the time is 167 divided by 60, and that would be 2.79 minutes. So almost 3 minutes. Okay, now let's put that to the test. Here I have the kettle filled with a half of a kilogram of water and a stopwatch, and I'll go ahead and turn that on. And now we wait. Okay, so that was 3.51 minutes, so about a minute longer than we were predicting. Probably the explanation for that is that this kettle, which is kind of an older kettle, is probably not a 1,000 watt kettle anymore. The power is probably a little bit less than that, which would mean that it would take a little bit longer. So I would say that we predicted pretty well, close enough, the time that it would take to boil that water. Here's our last calculation question. A 15.53 kilogram loose bag of soil falls 5.5 meters at a construction site. If all of the mechanical energy is converted into thermal energy in the soil, how much will its temperature increase? And for the specific heat capacity of the soil, use 840 joules per kilogram degree C. Now this is a little bit different in that what's going on is there is internal work being done on the bag of soil. The bag of soil starts off with potential energy, it falls, and that potential energy is converted into thermal energy through internal work. So let's see what you can do with this. Work on it, pause, work on it, and then come back when you're ready to see me work it. Okay, as I said, this one is a little bit different. Here, if I represent the energy as a box, what happens is the bag of soil has a height of 5.5 meters and a speed of 0. It falls down to height is equal to 0, but when it's on the ground, the speed is also equal to 0. So we have a decrease in potential energy. Our kinetic energy stays the same, but what happens is our thermal energy increases because there is a transfer, an internal work transferring the potential energy into thermal energy. So in this case, the change in thermal energy is equal to the decrease in potential energy. The temperature of the bag increases, so the mass times the specific heat capacity times change in temperature is equal to the initial potential energy of the bag, which is mass times G times height. And we're looking for change in thermal energy, so I'll divide both sides by mass times specific heat capacity. So these two cancel out. Notice that mass also cancels out, so the answer really doesn't depend on the mass of the bag of soil. The change in temperature is then equal to G times the height over the specific heat capacity of the soil. So the change in temperature is 9.81 newtons per kilogram. Our height is 5.5 meters. And our specific heat capacity is 840 joules per kilogram degrees Celsius. Okay, so change in temperature is, let's get our numbers, 9.81 times 5.5 divided by 840, and that would be 0.0642. And what are our units? Kilograms. We have 1 over kilograms and 1 over kilograms. Those cancel out. A newton times a meter is a joule, so those cancel out. We have 1 over Celsius in the denominator. We bring that up to the numerator, degrees Celsius. So the temperature of the bag of soil increases by 6/100ths of a degree. But that's important because the energy had to go somewhere. The bag had potential energy up high. It fell. As it fell, that potential energy was converted into kinetic energy, but it lost that kinetic energy when it hit the ground. So where did that potential energy go, the initial potential energy go? It went into thermal energy as a very small increase in the temperature of the bag of soil. Okay, here's a multiple choice question. Cooking pans made from which of the following metals would need less heat to achieve a certain cooking temperature? A, aluminum, which has a specific heat capacity of 920 joules per kilogram degrees Celsius. B, copper, which has a specific heat capacity of 390 joules per kilogram degrees Celsius. Or C, iron, which has a specific heat capacity of 460 joules per kilogram degrees Celsius. Okay, think about it. Come down definitely on an answer. Pause and think about it. And when you're ready, when you definitely have an answer, then come back and I will talk to you about this one. Okay, the physics here is that the heat is equal to the mass times the specific heat capacity times the change in temperature. And we are looking for the pan that will need the least heat. Well, if we assume that they have the same mass and we want the same change in temperature, the one that will have the smallest heat is the one that will have the smallest specific heat capacity. So we're looking for the answer with the smallest specific heat capacity, and that is B, copper. Okay, another multiple choice question. When you add heat to a substance, its temperature A always increases, B sometimes decreases, C might stay the same, D might go up or down depending on the temperature. Alrighty, think about it. Come down definitely on an answer, pause, and then when you have an answer, hit play again. Okay, when you add heat to a substance, two things can happen. One is its temperature could increase, or if it is a phase change, then its temperature would stay the same. So the temperature might go up and might stay the same. So the best answer here is C, might stay the same. The temperature doesn't decrease, so that's not B. It doesn't always increase, so that's not A. And D, might go up or down? No, it might go up, but it's not going to go down. So A, B, and D being eliminated, the best answer here is C, the temperature might stay the same if there is a phase change. Now, talking about phase changes, here's another question. The great cooling effect produced by water evaporating comes from its high, A, conductivity, B, specific heat, C, latent heat, or D, transparency. Think about that. Come down on an answer, pause, and hit play when you have an answer. Okay, when water evaporates, the relevant quantity is its latent heat capacity. So the great cooling effect produced by water evaporating comes from its high latent heat capacity, which is answer C. So C is the best answer here. Final question. The evaporation of water absorbs heat from the surroundings And the condensation of this water, A, does nothing, B, releases heat to the surroundings, C, increases the value of the latent heat of vaporization, D, decreases the value of the latent heat of vaporization. Please pause, think about it, come down definitely on an answer, and hit play when you have an answer. Okay, evaporation of water absorbs heat from the surroundings. Condensation of water, water vapor, is the opposite. So if evaporation absorbs heat, then the condensation releases the heat. This is what's going on when clouds form. Hot air on the surface of the earth evaporates water, so that absorbs heat. That hot air rises, and as that hot air rises up high in the sky, and that water vapor condenses back into water, which is what a cloud is. It's actually liquid water in the sky that releases that heat that was absorbed to the sky. So this formation of clouds is actually a method for cooling the surface of the earth and bringing that heat up higher into the atmosphere. So the evaporation near the surface of the earth, or off of you when you sweat, absorbs heat, and then as that hot air rises and that water condenses again, it releases heat up high in the sky. So the correct answer here is condensation of water vapor. B, releases heat to the surroundings. Okay, that was a lot of work. This has been a long lesson, but we're almost done with Unit 4. The next lesson is the final lesson. So I will see you then, and until then, think science.